But welcome. It's so nice to see so many people here today at the Worthing College. May I introduce you to our speaker here? Oops, and I've just...
Oop.
Right.
Don't worry about those.
And for my next trick, it's time for me to go now. David over here will talk about, well, he will tell you what he's going to be talking about. He's been working for Parker
Hannifin, yep.
Since 1989.
Yeah.
He's got a wealth of experience here about this area. We just happened to be talking in February. He just learned that he wanted a speaker, and he volunteered, just like that. If anybody else wants to volunteer to speak, please come and see me or David or Mike over here. And if anybody wants to be part of the committee to do all this, please see them as well. But without boring you even more and dropping more pens and things, let me go on to David. Thank you very much.
Thank you. Well, hello, and thank you for giving up your evening this evening to hear about the control of permanent magnet AC machines. I'm Dave Blood. I work for an American corporation called Parker Hannifin. I'm a technical staff research engineer. I think I got that right. And I work for Parker's Motion Technology Centre, which is actually in Cleveland, Ohio, but I'm actually based over here in the UK and live in Worthing, so it's all good. So this is our agenda. I want to talk about modelling permanent magnet AC machines, because if you want to control something, you really need to model it first, otherwise you can't really do much. I then want to talk about field-oriented control. If you know about AC machines, you might have heard the expression field-oriented control, and I'll explain what that actually means. And then if you're going to control a permanent magnet machine, and it's an AC machine, you need a source of variable voltage, variable frequency supply. So I want to talk about three-phase inverters, which is what we use, which is what that big metal box is over there. That was just it's a prototype from our lab. It's rated at about 125 kilowatts and has a maximum DC voltage input of around about 800 volts, and it's water cooled. At that stage, we'll get to the point where I'll present a block diagram of what a control system looks like for a permanent magnet AC machine, and we'll talk through that. And then I want to talk about another aspect of machines called field weakening. What does that mean? You know, can permanent magnet AC machines do that? And then we need to get on to the serious stuff, is what happens when things go wrong? I mean, permanent magnet AC machines are wonderful things. You may have noticed they're in lots of vehicles at the moment. They are small, they are powerful, they are high speed, everything you want for a vehicle. But you do have to treat them with care and know what you're doing. And finally, I was asked to do an opinion piece on this talk. So I thought I'd do an opinion piece on, you know, is electrification here to stay? Are, you know, electrified vehicles going to remain sort of like in the low percentage penetration of the market? Or are we actually going to see them take off and become the dominant sort of driving force for vehicles? So I have been provided with something to make the slides go backwards and forwards, but apparently laser pointers don't work on TV screens. So I have a 19th century laser pointer here, just in case I need to point something out. I also have my crib sheet down here, so you'll have to forgive me if I go to my crib sheet. So let's start. There's going to be about 30 slides, lots of pictures. There's going to be maths, but we're all engineers and we all love a good equation, so I hope that's okay. So here we have a picture of a permanent magnet machine. I'm going to have to use the laser pointer straight away. It's got 3 windings, and each winding has got a resistance, an inductance, and a back EMF. The windings are spatially separated by 120 degrees in a 3-phase machine, electrical degrees. And by convention, we normally call them UV and W, although I think UVW is a German convention. So, for example, V, U over here, IU over here, and etc. We're also going to make the assumption that the machine is electrically balanced. So the stator resistance is going to be the same on all 3 windings, the same for the inductance, the same on the magnitude of the back EMF. Although the quantities flowing in the machine, like the currents, are sine waves, they're sinusoidal, and they're all phase shifted from each other by 120 degrees. And the final assumption we're going to make is there's no fault in the machine. So there is no false circuits or currents going to earth. If I take the three currents and add them together, Kirchhoff's law says they're going to be zero. So when you look at that, you think, gosh, how am I going to model that? Is that a nice thing to model? Well, it's not particularly nice, to be honest with you. So the first thing we need to do is simplify what we're doing. And it turns out it's much nicer and easier to work with an equivalent two-phase machine than it is a three-phase machine. So that's what we're showing here. We've got a three-phase machine and we're going to move it to an equivalent two-phase machine. Again, by convention, if we've got a two-phase machine, we normally call the windings alpha and beta. Alpha is on the x-axis and beta is on the y-axis. The components stay the same, although there are different sorts of transformation you can do. And again, you're going to get sinusoidal quantities flowing, like currents flowing in those windings. But in this case, as it's a two-phase machine, they're going to be sine and cosine waves. So the sine waves are 90 degrees phase shifted from one another. So how do you do that? Well, you need a transformation. Here is an example of a transformation where we take quantities that are normally three-phase quantities. So you can imagine you've got something like IU, IV, IW on one side, and you do the transformation and you're going to get I alpha and I beta on the other. So the maths is there. If you were to make a simulation of that or just write a little program to test it out, if you put three sine waves in, 120 degrees phase shifted from one another into that, you will get a sine and cosine wave coming out the other end. Quite good. And where there's a transformation in one direction, there's one in the other direction as well. So here's an example of where I've got sine waves and cosine waves, I alpha, I beta, and I'm going to transform it back into a three-phase system so I get the three-phase currents out of it. The maths is there. It's quite simple, and the reason why I'm introducing this now is these symbols will turn up later when we look at the full block diagram to control the permanent magnet AC machine. Okay. This slide is actually quite important because there's another transformation that unfortunately we have to do. If I looked at the diagram on the left-hand side, you can see I've got my alpha and beta windings or axis, and I've got current flowing through them. You can see them, I alpha and I beta. And in a sense, because they're at right angles to each other, I can make a vector out of that. I can actually find the current magnitude by doing a bit of Pythagoras. And I've denoted that by this current vector IS, just over there. And if I had, for example, I alpha as a cosine wave and I beta as a sine wave, and they're of the same amplitude, then I would get a current vector of constant magnitude, and it would rotate, in that case in the positive direction, at the electrical frequency. All makes sense? And now I'm going to introduce two more axes, and you can see them, and they're rather special. We call them D and Q, direct and quadrature. And the difference between these two is the alpha and beta axes are stationary, they're not moving, but the D and Q axes are rotating. They're rotating at the electrical frequency. So if I can take that same current vector and now project it onto the D and Q axis, I'll end up with two more currents, ID and IQ. And because the current vector is rotating at the electrical frequency, and because the D and Q axes are rotating at the electrical frequency, those projections will be DC quantities, and they'll be related to the amplitudes of sine waves. So this is a mechanism, this rotational transformation, whereby I can turn the sine wave quantities into DC quantities and make my control problem a whole lot easier. So it's a good idea. There's one other thing happening in this slide, and it's in red. And that is, if we choose, I could align the D-axis of this rotating set of axes, I could align it with the permanent magnet in the rotor of the machine. And that's known as field orientation. So when you hear people talk about field-oriented control, this is what they're talking about. A set of rotating axes, D and Q, a rotational transformation, and the D-axis aligned with the real magnet in the machine. Now, it turns out, for a permanent magnet AC machine, I can go measure the position of the magnet. All I need is some sort of absolute position device, like an absolute encoder or a resolver. I have to do a bit of calibration so I know where 0 point is, but you can do it. You just go measure it. And that's denoted by this angle here, rho. Oh, excuse me. So I measure it, I do my rotational transformation, I've got my D-axis aligned with the magnet, and that's all very good.
Question.
Yes.
Are you assuming rho is constant, or so it's rotating it effectively synchronously at this point?
The permanent magnet AC machine is a synchronous machine.
Right, okay.
Yeah, it's not an induction motor. It's a bit like...
Yeah, but if it wasn't rotating synchronously, I think your equations might have a bit of a problem here.
You can do vector control of induction motors as well.
Right.
You have to take into account the slip,
Yeah.
but it is entirely possible. And the same theory applies. You can actually have a rotating set of D and Q axes aligned with the field that you induce in an induction motor. It's entirely possible. Okay. I spent the early years of my career making induction motors work with vector control. I quite like induction motors. They're really good. They've got lots of good properties. Unfortunately, they just can't match the power density of permanent magnet AC machines, which is why you don't see them very often in vehicles.
Okay.
I mean, the early Model S from Tesla had a rather special induction motor. I think it had cast copper rotor bars or something like that to try and improve the efficiency. But now everything is permanent magnet AC motors, pretty much.
Can I just ask, how do you work out where the rotor alignment is at any one time? Is there a separate sensor or
No,
tacker or
no,
separate motor? Or?
no. You measure it. You have an absolute position encoder. You put on the shaft.
I see.
Yeah, you measure it. You measure the position of the
So
shaft.
it is an extra feature of the motor?
Yes.
Okay.
Yeah. We could talk about sensorless vector control, but that would be a whole other lecture. I mean, it's just... I had to cull this down to 30 slides. I'm sorry about that. Maybe that's a talk for another time. So what does those transformation look like? Well, they look like this. You can see on the left-hand side, I could put in sinusoidal alpha and beta currents. I could put in my field angle underneath it, and then if I follow the maths that's on the board, then out will pop my D and my Q axis currents, all nice and simple. And then, just because of symmetry, there's one that goes the other way. Ooh, hopefully. Ah, yeah. So one last thing to say about this, by the way. Because we're going from sinusoidal quantities to DC quantities, we sometimes just call that demodulation for obvious reasons. The opposite transformation goes from DC quantities like ID and IQ back to the sinusoidal quantities I alpha, I beta. For obvious reasons, we call that modulation. You'll be glad to know those are all the transforms you need to know to control a permanent magnet AC machine. So we got the hard bit over. Okay. And now I want to talk about different types of AC machine. These are both examples of interior permanent magnet AC machines. You can get permanent magnet machines where the magnets are actually on the rotor. They're normally glued on the rotor. I've seen some where they glue the magnets on the surface of the rotor and then have to put a sleeve over the top, because when the motor's spinning, you don't want the magnets to go flying out. That would be a bad thing. But if you bury the magnets inside the rotor, they're going to stay put. And we've got two different types of design here, and they're important. So this particular design is you can see the magnets in green. They're arranged like the spoke wheels of and it's called a spoke wheel design, as you can imagine. It's a very smooth magnetic circuit. There is no points along the periphery of that rotor where it's, the field isn't smooth. And because of that, we call that a non-salient pole design. There's no magnetic preferred path. And when we look at the transient equivalent circuits, which we're about to do, of these motors, you will find that means that the inductance you see on the equivalent circuit for the D-axis winding and the inductance you see on the Q-axis winding are the same. And that makes your life a lot easier when it comes to controlling motors. There's another type of motor, and you can see over here with this sort of V shape, that has preferred paths for the magnetic flux. And as such, we call that a salient pole design for an interior permanent magnet motor. And the upshot of that is, when you look at the transient equivalent circuits on the D-axis and the Q-axis, the inductances are different, and that's significant later on. We make both of those. In fact, that's the older design, the spoke wheel design, and the one with the V shape is the more modern design. There's actually less magnet in the V-shaped one than the spoke wheel one. It's less hungry for magnets, which is why people prefer it, because magnets are obviously expensive. Ooh, let's move over here. So here are the transient equivalent circuits for a permanent magnet AC machine. If you look at the voltage equation, it's kind of easy. There's voltage, there's resistance, there's a rate of change of flux. Well, that's kind of what you would have expected. And then you've got these things, these cross-coupling terms where you've got somehow the D-axis flux affecting the Q-axis voltage and vice versa. Where on earth did they come from? Nobody ordered those. It happens when you take the equivalent circuits in the stationary alpha and beta axis and you do that vector rotation, you naturally end up with these cross-coupling terms. It's just the way it is, and you just have to live with it. There's then another equation down here that shows it's a synchronous machine. So the electrical frequency is glued to the mechanical speed or frequency by the pole pairs of the motor. If you remember the previous picture, the spoke wheel design had like 12 magnets arranged as spokes, so it was a 12-pole motor or 6-pole pair. Whereas the V's, there were 6 of those, so that's a 6-pole motor of 3-pole pairs, and that P there is the number of pole pairs of the machine. And then you've actually got the flux equations. So the first thing to notice, we're field oriented, therefore the magnetic flux of the permanent magnet is on the D-axis, and then we've got the flux produced by the inductance and the current. Whereas on the Q-axis, you've just got the flux produced by the inductance. So far, so good. And you can see I've drawn that up as a little circuit diagram with, a flux, a voltage proportional to speed and flux, or back EMF, and the 2 cross-coupling terms. And then the rest of it is just an RL load, to be honest with you, with very little R. I mean, if a motor had a high stator resistance, that would be a bad thing, because it would be a very lossy motor. If I substitute in those flux equations, you'd end up with the standard sort of equations now. You probably recognise things like inductances and rate and change of currents, cross-coupling terms, and a back EMF. So if I was to look, well, this is probably dragging people back a bit, steady-state phasor diagrams for AC machines. If you remember those? So if I was to look at a non-salient pole type machine, imagined it was running at some speed, imagined it was at some load, what would the various currents and voltages and how would they relate to each other? And you would end up with a diagram like this. Now it turns out for a non-salient pole type machine, the spoke wheel machine, we would want to control the D-axis current to be 0. And we'll talk a bit more about why that's a good thing later when we talk about torque equations. And we would only control the Q-axis current, but in terms of the phasor diagram, you always start off on the D-axis. You can see we've got the permanent magnet flux that's glued to the D-axis. We're field oriented. You can see we've got a back EMF term which leads, because we're rotating in a anti-clockwise positive direction, that leads the flux, so that makes sense. we've got some Q-axis current, and then we've got the voltage drops due to the inductance and the resistance, and then the voltage that we're applying makes up the rest. It's actually quite a simple looking phasor diagram. It's actually quite nice. What happens with the machine which has got V magnets in it? What does that look like? Unfortunately, it's more complicated. So it turns out that if you want to maximize the amount of torque you get from the machine for the amount of current you put in it, unfortunately, I have to start introducing some negative ID current. And we sometimes call this phase advance. If you ever hear about people talking about permanent magnet machines and phase advance, that's what we're talking about here. We independently control the currents on the D and the Q axis, but we have to add a bit of phase advance as the torque increases to try and maximize the torque we get out of that type of machine for the current that we're actually putting into it, for the current magnitude we're putting into it. It's a more complicated machine to control, but it has some advantages. Torque equations. This is probably the most complicated slide, by the way, with the most equations on it. But anyway, here goes. In an AC machine, a bit like a DC machine, you know, we've got current vectors, we've got flux vectors. We've seen those now in our phasor diagrams. Torque is always the cross product of a flux vector and a current vector. And that's what that is there. If you do the maths, you'll end up with an equation that looks a bit like that, which is a bit strange. You know, you've got d-axis flux times q-axis current minus q-axis flux times d-axis current. And that looks rather horrible. If I then substitute in the equations we saw a little bit back for the d and q-axis fluxes, you'll end up with this thing over here. But I can break that down now, and I have done, into two components. One I'm calling TEM, and the other one I'm calling TR. And EM stands for the electromagnetic torque, the torque due to the magnet, and the other one is the reluctance torque. So, the electromagnetic torque is exactly as you would imagine it. I've got a vector of flux, I've got another vector of current at right angles to it. That's the torque. It's that simple. There's nothing more to think about than that. But you'll notice that this reluctance torque is a bit strange. It's proportional to the difference between the inductances on the equivalent circuits of the D and the Q axis and the products of the D and Q currents. For a non-salient pole machine, if you remember, because it's such a smooth magnetic circuit, the LD and the LQ are the same. The inductances on the D and the Q axis, all circuits, are the same, and therefore that term goes to zero and there is no reluctance torque. Makes your life so much easier. So machines like the spoke wheel design machine, they may be an older design, but they are really easy to control. Don't have to think too hard about it. Machines like the V-shaped, I showed you, the salient pole design, need a bit more thinking about as to how you would control it. They're more complex. The reason why people like these salient pole machines is because they like to try and make use of this reluctance torque. It's free torque. I didn't need to buy a magnet to make that torque. It's just the way I've shaped the magnets and loaded them into the rotor that allows me to make use of it. So as long as I know how to do that, I'm going to get more torque out of the machine for less magnets, and everyone likes that idea. Okay, so that's just a summary slide. I'm not really going to talk much about non-salient pole motor control. One more slide on that. I'm really going to concentrate on this easier spoke wheel design, non-salient pole type machine. We've got some equivalent circuits now where quantities flow around as DC currents rather than AC currents. We've only got two of them rather than three. And it kind of makes sense. A resistance, an inductance, a back EMF, and then unfortunately these strange cross-coupling terms that came out of the process of going from a stationary reference frame to a rotating reference frame. But the best bit is torque is proportional to current. Makes your life easy. So if we are going to control current, we're going to have to make current control loops. We're going to have current demands, we're going to have some sort of regulator, some sort of current feedback, and then in practical reality, some sort of device that's going to make us variable voltage, variable frequency supply, AC supply. Now, if all you need is a few watts of power, you could probably get away with some sort of linear amplifier. That'd be fine. But any sort of significant power, hundreds of watts and above, or 125 kilowatts, you need to have a high efficiency switching amplifier. And for inverter control, permanent magnet, in fact, any three-phase electrical motor control, we go to a three-phase, two-level inverter. And here's what it looks like if you've never seen one before. You've got 6 power switches, and they're arranged in 3 totem poles, one on top of each other. And we've got some freewheel diodes that are in parallel with those switches. The connection to the motor, the U, V and W, is in these midpoints, and we just wire that directly to the motor. In fact, if you look at this later, that's the 3-phase output, that's the DC input. And then we're going to have some sort of DC link here, which we have some capacitance on it, and then we have a DC supply, which in this case is a battery. If you think about it, I can either connect one of these phase outputs to the top of the DC link or the bottom of the DC link, and that's why we call it a 2-level inverter. There are other topologies which have more steps. You can get 3-level inverters, 5-level inverters. They have more power switches, which is a compromise between waveform quality and cost. But this is typically what you would find in most industrial applications, in fact, most electric vehicle applications as well. Why do we have the diodes? Why do we have the capacitor? Well, we're going to be switching into an inductive load, the windings of the machine. As you know, once you've got current to flow in an inductor and then you try and stop it, that's usually a bad thing because it's going to generate whatever voltage it needs to carry on making the current flow. So you need some path to allow that current to flow back into the power source when you've been switching it. And that's really the job of these freewheel diodes and the capacitor. Just as a reminder, we started off this lecture saying we had a 3-phase machine and that we had 3 windings that were spatially separated by 120 electrical degrees. And we've just said that we can either attach one of these windings either to the top of a DC link or the bottom of a DC link. If you imagine I could take my battery and I could split it in 2 and put as a notional 0 volts point in the middle, okay? Then if I was connecting my, say, U phase to the top of the DC link, I'd have positive voltage on it. And if I connected it to the bottom of the DC link, I'd have negative voltage on it. And because these windings are spatially separated, you can think of these voltages having not just magnitude, but direction. And that's what this little diagram is meant to show here. That's the U phase connected to the top of the DC link. That's the U phase connected to the bottom of the DC link. And you can do it for the other phases as well. So the question is, what could you do with that? Well, here's an example of where I have connected the U phase to the top of the DC link. So I've got half the DC link voltage pointing that way. And I've got the V and the W phases connected to the bottom of the DC link. So I've got minus half the DC link on those 2. And if I use my handy diagram, you would end up with these vectors. If I did a vector sum of all of those, I would end up with a single vector pointing in this direction, and its magnitude would be the DC link voltage. I've denoted that as being V1, And I've given it a number, 1, 0, 0. 1 meaning the U phase is connected to the top of the DC link. 0 is meaning the V and the W are connected to the bottom. It's kind of obvious to say, when you're talking about the legal possible states you can put the switches in, never turn on the top device and the bottom of the device together at the same time. That's generally thought of as being bad and will obviously result in the destruction of your power electronics in your inverter, and we call it a shoot through. So it turns out, if you look at all the possible legal, non-destructive combinations of those power switches, I will end up with 6 vectors, and I've denoted them here, V1, V2, V3, there's 6 of them, and you can see the switching states now associated with them. They all have the same magnitude, they're all spatially separated by 60 degrees, which is quite cool. There are 2 other possible legal switching states you can have. I could switch them, all the switches to the bottom of the DC link. That's perfectly legal. Sometimes it's called a 3-phase short lower, because when I've switched them all to the bottom of the DC link, I've shorted all the windings out together. Sometimes it's known as a 0 vector, because there's no line-to-line voltage when they're all connected together on the bottom of the DC link. Sometimes it's known as a pause state. And then there's another one, V7 here, where they're all connected to the top of the DC link. But it's the same deal. There's no line-to-line voltage, so we call it a 0 vector. If I wanted to create an AC supply just doing this, I could just clock around them. I could start off and spend a bit of time doing V1, then I could go to V2, V3, all for equal amounts of time. The less time I spend doing that, going around, I would create some sort of AC voltage waveform on the phases of my motor. And the motor hopefully should start to spin. If I wanted to change the amplitude of the voltage vectors I was applying, I could, for example, let's just take this one, V1. If I could just take that one that's turned on there and turn it to a 0, one switch change, I could take it to V0. So I could spend a little bit of time at V1 and then some more time at 0 with no line-to-line voltage. With V2, just change that one to a 1 over there, and I could go to V7. And again, I could apply the voltage vector for a bit of time and then take it away again. And I could pulse width modulate these things as I'm actually spinning them round. That is actually a very legitimate way of making an AC supply out of a 3-phase inverter. It's called 6-step control. Parker have an aerospace division, and I know for a fact they use 6-step control on some of their aerospace inverters in aircraft. It's a legitimate way of doing things. It's a simple way of doing things. It has a slight drawback in the fact that, as you can imagine, it's not producing beautiful sine waves of voltage. And as a result of that, you end up with a current waveform which has obviously a fundamental current of fundamental component of current, but is rich with harmonics, which means you've got quite a bit of ripple current. You're going to see some extra copper losses as a result of that, and your total efficiency in your system has gone down. But it's simple. Nothing wrong with it. Oops. A better technique would be something called space vector modulation. What on earth does that mean? Well, what it tries to do is synthesize a voltage vector of whatever desired amplitude you want at whatever angle you want, and you do that by choosing 2 adjacent voltage vectors. So here I've got some sort of voltage vector that's sitting about there. I'm going to apply V1 for a little bit of time, and then I'm going to apply V2 for a different amount of time. And if I scale these voltage vectors by the amount of time I'm actually switching them over a certain period of time, I will end up synthesizing this average voltage vector. It's a pretty cool idea. And it works very well. In fact, when I first started work a long time ago, 1989, that was the first job I was given. Go and make yourself a space vector modulation system for an inverter that we want to launch in a few months' time. Okay, I can do that. So how do we do it? Well, you can do it using a modern microcontroller, using the very common peripheral in a microcontroller called a general purpose timer. And in a general purpose timer, what you will probably find is you can have a sort of triangular, well, it's not a sawtooth, it's a triangular carrier waveform, which you can see here. And then there will be comparator levels that you can program. And when the carrier waveform goes through a comparator level, you get a change in a switch somewhere, okay? What will happen is it will fire off a peripheral pin on the microcontroller. You can send that to a gate drive circuit, and that will tell a certain transistor to turn on or off. That's how it works. So here you can see the pattern starts off where we're at 0, 0, 0, or the three-phase short circuit lower. And then at a certain period of time, we turn on for a period of T1 just by switching one switch. It's pretty cool. And then after that, as the waveform rises, we'll get to another comparator level and we'll switch on another switch, and that will give us V2. And then finally, we'll hit another level and we'll turn everything on and we'll be at V7. And then, because it's a symmetric triangle wave carrier, we'll reverse that process going out the other side. In a typical inverter, let's just take this one. This one will switch anywhere between 4 and 8 kilohertz, something like that. So you can imagine at 4 kilohertz, you know, what the period is. It gives you a feel for it in terms of microseconds. Every single switch point here is actually two switching events happening. It's one power device turning off and its complementary one turning on, or vice versa. Every time you switch, there's a little bit of loss that occurs in the power converter. So space vector modulation is good, but it is a little lossy, okay, a little bit. It's more lossy than 6-step, but it does make a nice waveform. So for example, in this half a carrier period I've drawn, you've got 6 switching events taking place. That's kind of cool. What does that all look like? Well, this is a Simulink simulation. If I looked at those, well, in fact, one thing, you may have noticed that the time I spend at, the V0 vector is the same time I spend at the V7 vector. The pause times are the same, and that's important. When you do that, if I looked at the comparator waveforms, and you can, here's a simulation, you get a very characteristic looking waveform. And it's got this sort of double hump to it, and that does not look like a sine wave. What's going on there? Well, it turns out if you look at the harmonic spectrum of that, what you will find is it's got the fundamental, but then it's full of tripling harmonics. So I'm going to get this right, in a, what is it, half wave odd symmetry, that's what a sine wave is. If you look at any sort of waveform that's got that sort of property, you will find that there are no even harmonics, okay? But tripling harmonics, if I have a 3-phase system, any harmonic that is an odd harmonic multiple of 3, they cancel line to line. So when I take these two waveforms, take any two of those waveforms and subtract them from each other, what I'm left with is a beautiful sine wave. It's just a factor of space vector modulation. It's quite a cool thing to see when it's working correctly. Okay, we've got to the block diagram bit. So here's our control block diagram, and I hope you can recognize some of the symbols, although it's a bit of an eye chart, of a control system for a permanent magnet AC machine. So I'm going to start off over here. I've got this as a speed loop, so I've got some speed feedback, speed demand and speed feedback. I've got a PI regulator. Honestly, I don't really use anything more than a PI regulator. In this one, I've got a little switch, so I can switch it between speed control and torque control. It depends on your application. If I'm driving a hydraulic pump and I want to control flow, I'm going to be in speed control. If I'm in a traction application driving a vehicle's wheels, I want to be in torque control, and I'm the speed control. I'm the guy sitting there with his foot on the accelerator pedal controlling the speed. The output of that will be a torque demand, which typically we would put through some sort of torque limits. And then, because we're controlling a non-salient pole type machine, I can just convert that torque demand through a scaling factor straight into Q-axis current demand. Nice and simple. I'm then going to have another limit, which is going to limit the amount of current that's flowing. So I've now got limits on torque and current. And then we'll get to our current loops, and you'll see that I've got my Q-axis current demand going straight in, and I've got 0 for my D-axis current demand because I don't want any. So I'm going to move over to the other side now. Over here, I've got my absolute position measuring device, either an absolute encoder or we use resolvers, doesn't really matter. I'm going to get my speed feedback from that, which is going to go over to my speed loop. I can then take the mechanical angle, multiply it by the pole pairs, if you remember that equation, and that's going to give me my field angle, rho, which I'm going to use in two ways. Down here, I'm going to have a current transducer. That's my terrible drawing of some sort of current transducer, like a LEM current transducer or something like that. Technically speaking, if the machine is balanced, I don't need to measure all three phases. I can actually get away with just measuring two phases and save myself a bit of money. But I'm going to treat it as though I've got three phases and put it through some sort of transformation that takes it from a three-phase system into the alpha-beta two-phase system. I'm then going to use my field angle to do the rotational transformation, remember that one? And that's going to give me my ID and IQ feedback, which I'm going to use in my current loops. Going back over to the current loops, they're just PI regulators. But you can see here that I've added some little terms. Those are feed-forward terms to get rid of the cross-coupling effect that you get, okay, when you try and do control in this rotating reference frame. I could have put in another feed-forward term on the Q-axis for the back EMF. It's perfectly legitimate to do. Or if you've got a PR regulator, you can just let the integral term track the back EMF. That's also acceptable as well. And what's going to come out of that is voltage demands. These are going to be in the D and Q reference frame, so they're VD and VQ. So I have to do the process again in the opposite direction. I have to take those, I have to modulate them. So I take my field angle that I've measured, I put it first through the thing that goes from D and Q to alpha and beta. I then need to move those into a three-phase system. So I go from alpha and beta into VU, VW, VV, and those help me make the comparator levels that I actually put into my, my general purpose timer unit. Just hopping back a couple of slides, I forgot to mention, when you do this process, I will get a nice sine wave, but if you look at it on a scope, superimposed on top, you will see sort of triangular ripple current sitting on top of the sine wave. And that's perfectly natural, it's all part of the PWM process. But if you're trying to close a current loop, I don't want to see any of that ripple current appearing in my current feedback. That's not good. So how do we get rid of that? Well, it turns out if I sample my currents at the top and the bottom of the triangular carrier wave, I will actually sample the underlying sine wave. It's magic. Okay, and I don't need to do any special filtering. I just have to synchronously sample in the right place. And you can do this. You can get these general timer units to trigger interrupts at the top and the bottom of the carrier waves that you can then trigger another peripheral, which would be the analog to digital converters. And when you look at those signals, you will see nice sine waves of current. You won't see any ripple current, which is kind of good. So that's a fairly simple sort of block diagram of what a permanent magnet motor controller does. They do get more complicated, or can do, but those sort of building blocks with those transformations are the foundations of trying to control those motors. It's not the only way to do it. Ooh, motor mapping. Sometimes people call it flux mapping. But the idea here is, why don't I just go and measure it on a dyno? You know, and we have a sister company or a company part of Parker Hannifin called Curtis Instruments. They've got a research centre up in Newcastle. They have dynos, and what they do is they will run customers' motors. They don't know what motor they're going to get, to be honest with you. They put it on their inverter. And this is an example of it. They will run the motor at a certain speed, usually below base speed, which we'll talk about next. And then they will scan through, you know, ID and IQ. They'll start off with lots of IQ and no ID, and then come through a circle and look at, measure the torque as you sweep through ID and IQ. And it will maximize somewhere. You will get a point of maximum torque coming out of this thing for the amount of current that you're putting in. And that's what these green dots are. And from that, you can build up lookup tables. Okay, this is actually a very successful control scheme for salient pole type machines. And I know some businesses who will charge you lots of money when you give them their motor, your motor, to put on their inverter, to get a report that looks like that, that will tell you what, you know, where, for a given torque demand, what values of ID and IQ current you need to command in order to get maximum torque. Just for completeness, if you're wondering, these sort of contour line things are contours of equal torque. But you can do it that way. Okay.
Just on that one, will the characteristic drift very much over time?
It will drift with temperature. And not time necessarily, but well, unless if the magnet demagnetizes or something like that, then it would drift over time. But assuming there's no demagnetization, the other effect that changes the strength of magnets, which is temperature, can have an effect on this. So I've known people who do things like that, that you end up with 3D lookup tables to take into account the temperature as well, to try and, because it turns out for traction applications, it's really, really important that if you say, I want 10 Newton meters, the thing produces 10 Newton meters within a reasonable accuracy. You don't want it to drift particularly. So yeah, traction applications, especially on vehicles, tend to be quite demanding, or can be. Depends on your vehicle. Let's talk about field weakening. So here I've got a picture of a motor torque, maximum motor torque that you can get. And we all know electric motors. If you've been in an electric vehicle, you put your foot on the pedal, you get instant torque at 0 speed. It's quite exciting, really. So you've got all this torque available to you, and generally speaking, you can have it all the way up until you hit something called the motor base speed. And I'm going to use the example of a permanent magnet DC machine. So if I had a permanent magnet DC machine, and I put some voltage across the armature, current would flow, I'd get some torque, and the machine would start to accelerate. As I start to accelerate, I'm going to get a back EMF. And that's what you're starting to see here, that the voltage you see on the terminals of the machine would have to rise continuously as the speed goes up. And you can carry on with that process right up until the point where the back EMF equals the battery voltage. And then that's it. You can't go any faster, you're kind of stuck. If I had a wire, you know, a separately excited DC machine with a field winding, I have more flexibility. I could, for example, reduce the field current, reduce the magnetic flux in the DC motor, reduce the back EMF, so for the same voltage, I can now go quicker. But because I've reduced the flux in the machine, I've changed the torque constant, so for the same current, I can't get the same torque anymore. And you tend to find you have this curve here where the voltage of the machine stays constant, but the torque starts to drop off. And the point at which this happens, we call the motor base speed. And for obvious reasons, we call this region the constant torque region. And because this is kind of like a 1/over frequency type thing, we call that the constant power region. And the big question is, can I field weaken a permanent magnet AC machine? Because you can't do that with a permanent magnet DC machine. Well, There's 3 diagrams here, and you probably recognise the phasor diagram that we looked at earlier. So here I've got a machine operating at its rated speed, and the maximum voltage is denoted by this black circle. And you can see here the yellow arrow, the terminal voltage, is equal, it's touching the black circle. I've reached base speed, okay? The back EMF, the red part, is less than the maximum voltage. It's kind of good, but it's a pity because we can't go any faster. The one in the middle would be, well, if I started operating beyond base speed, then I can't achieve it because I can't make the volts, because the yellow arrow for the volts is outside the black circle, and oh dear, my back EMF just got bigger than my possible rated voltage. That's not necessarily a good thing. But there is a trick. And again, it involves adding some negative D-axis current. If I were to do that, then I'd kind of tip over this part of the phasor diagram. And my terminal voltage would still be on the black circle. I'd still be producing full volts, okay? But it would at least allow me, as I start to produce more negative ID, it would allow me to go quicker. The downside of that is I'm kind of wasting current. I had all this current that I'd hoped to make torque, but now I've got to have to make it making negative ID current uselessly. I'm not getting much torque out. I'm getting no torque out of that. So I'm losing the ability to make torque. So I am going to see that sort of field weakening drop off in torque when I do that, okay? But here's the rub, which is, look at the back EMF. It's getting much bigger. We call it field weakening, but actually the field is not weakening one little bit. The field is the same. It's a permanent magnet. Now that would not be true if this was an induction motor. With an induction motor, you induce the field. When you go into field weakening, you genuinely weaken the field off. That's not the case with a permanent magnet motor. And therefore, the torque equation, which basically says torque is proportional to the permanent magnet times the Q-axis current, that stays the same even when you're in this field weakening type operation. It's a geometric trick, but it's a very clever one. So in essence, can you field weaken a permanent magnet motor? Yeah, you can sort of, but actually you're not really weakening the field at all. And that has implications. What happens when things go wrong? So, as I said, permanent magnets machines are wonderful. They're small, they're energy dense, they go really fast, people love them, lightweight. But they do pack a punch, and you do need to be careful when things go wrong. So when things go wrong, you generally speaking in any system want to go to a safe condition, a safe state. And there are 3 of them. So you've met some of them before, but the first and obvious one is 6SO, 6 switches off. Just turn off all the switches in the power converter. If I was operating less than base speed, and let's say I had a trip event, I don't know, the motor got too hot and we need to stop operation, then it's perfectly legitimate to turn off all the power switches. In that condition, the back EMF is lower than the battery voltage, no current would flow back into the power converter, the motor would coast, everybody would be happy. That's okay. Let's play that game again, but let's say this time I was operating just into field weakening and I had my thermal trip on my motor. I turn everything off. Well, now my back EMF is bigger than my battery voltage. And I've got a 3-phase rectifier through these freewheel diodes. So what happens is you start to rectify the back EMF, you get uncontrolled current flowing back into the power converter into a high voltage battery. That means I'm doing work. So that translates as lots of braking torque on your motor. So if this particular motor was, say, a traction motor and it was on some sort of single speed gearbox with no clutch, and I was running down the road at some speed because I'd been field weakening, I tripped and went into the 6 switches off condition, my wheels would lock up. That's not good. In fact, that's very bad. So there are some other safe states. And you've already met these, the three-phase short circuit lower, where we basically short the motor out by turning on all the bottom power devices, or the three-phase short upper. If I play that same scenario again, but rather than go to 6 switches off, I go to one of the three-phase short circuits, then effectively what I'm doing is I'm placing the back EMF across the inductance and the resistance of the machine. Okay? When you do that, you get to see the three-phase short circuit current. Sometimes this is known as the characteristic current. It produces at high speeds a very slight braking torque, but it's perfectly balanced. It has a big initial transient and it settles down to some sort of steady state value. This happens to be a simulation I did on Simscape in MATLAB Simulink, just so you could see it. But that braking torque would be the same in a low value right up until the point that you're getting to be at very low speed, and then it will maximize to something quite big. So that scenario, you'd be slowing down, and all of a sudden, just before you get to 0 speed, you'll come to a juddering halt. Again, not particularly wonderful. If you had the ability to know what the speed was and be able to go from a three-phase short circuit to a 6 switches off at a low enough speed, you could avoid that problem. There's one more thing to say about this. Three-phase short circuit currents generally are much higher than the rated current of your motor. Okay? Sometimes an awful lot higher. I mean, typically figures of 140%. We've seen some examples of almost like 200%, something like that. So here's the warning. You know, if you go around and you basically look at the rated current of the machine, the rated current of the inverter, you match them, and you go off and you do your application, and let's say you were field weakening and it just happened to have a 200%, you know, short circuit current, and you go into one of these three-phase short circuits, which is a good thing, by the way, because we know that now, that could be really bad for your inverter. Your inverter might not be able to cope with that much current, and you will destroy it. And I've known people do that. It's really important to know what your three-phase short circuit current is of your motor, and to make sure the inverter that you're applying here is capable of withstanding that current. If you thought that one was bad. Ooh, what would happen if I, for whatever reason, I had a failure of one single power switch? What would the fault current look like then? So I think one of the first people to study this was Professor Thomas Jahns from the University of Madison, Wisconsin, the WEMPEC consortium. And he called it an asymmetric single-phase short circuit. And it's got a really characteristic current. It's very strange. This is zero current. You get two phases pushed down, and you can see they're clipped at the top. They're not sine waves anymore. They get clipped. They don't go in the opposite direction, and the other one gets pushed up. The thing to understand about this, if you thought the three-phase short circuit current was bad and could get very big, this is a monster. This is much bigger. Okay, this is terminal for your inverter within probably 40, 50 milliseconds, something like that. If you have the ability to detect that, okay, your best course of action is to somehow convert it to a suitable three-phase short circuit, because it's lower and you've very sensibly rated your inverter power electronics to deal with the three-phase short circuit. The really scary thing about that one is that could actually occur even if you were operating below base speed. Let's just say I was operating below base speed. I lost a switch. I got that. Okay, I don't have to be in field weakening to get that fault current flowing. So it's important to know that your inverter can deal with that situation as well. Scary stuff. There's actually one more, but I didn't put in this, but I'll tell you about it. You can get, again, very rare, but you could get, if I had a wire wound machine And you know how those are made. You kind of pull the wires through the slots. You'd never really know which wire is next to which other piece of wire. It's called a wound and round machine. If I was to have a breakdown of insulation between, not between the wires and the actual rotor or anything like that, because that would be a hard short circuit, okay? But if I had it between windings inside the machine, then I will get a really large current that just flows around that. I've got a permanent magnet, I've got kinetic energy, and it will fry the winding. And I think it's an area of active research as how best to deal with that kind of fault. I was asked to do an opinion piece. We're on to the last 3 slides. Not too bad. Is electrification here to stay? And I thought I'd answer that in 3 slides. And the first one is, let's look at the oil price. So I grabbed these off the internet. This is a graph of the oil price since the first oil shock of the 1970s. This is actually a logarithmic scale. So that's why I had to put $108 there. And this goes back to like 1973, and I'm old enough to remember that. And I remember my dad lamenting, oh my goodness, petrol's going to be £1 a gallon, you know. But you can see world events, you know, the 73 oil crisis, the Iranian Revolution, the first Gulf War, Russians' invasion of the Ukraine, what we're currently going through. My favourite's this one. The 2008 financial crisis. I think it's fair to say that interest in alternative means of, you know, traction, whatever, away from petrol and diesel, always you get real interest when the price of oil is high. It stands to reason. In 2008, that peak there apparently was $140 a barrel. It's quite a scary number. And I was talking to a manufacturer of inverters for mobile applications, and he said just around about there they had huge interest in, you know, what they were doing. They had projects, people were proposing, people were beating a path to the door, they had everything. And the next minute we had the financial crisis, the oil price plummeted, and those projects were either delayed or, you know, project timelines or projects put on hold or just cancelled altogether because they were no longer economically viable. So in some sense, over this time period, you could argue that the electrification of our vehicles has been hostage to the price of oil. It kind of makes sense. But it's not just the price of oil. You have to have cost-effective, technically capable electrification solutions. Here's another graph I pulled from the internet. So this is the price of lithium-ion batteries packs over the past, I don't know, 2013 to 2025. Around about that time, I was working for a bit of Parker. We were trying to create containers full of lithium-ion batteries and grid-facing inverters to basically absorb intermittent renewable energy and promote the use of renewable energy on the grid. And I remember prices not as being $827, but more like $1,000 a kilowatt hour. Look at the price now. Approaching $100, probably is $100 a kilowatt hour, probably even cheaper in certain parts of the world. This is a typical power curve. You see these when you have technology coming into the world and the economies of scale just make it cheaper and cheaper and cheaper to make. It's very typical. I could probably pull another graph off the internet about the price of solar panels and it would look pretty much the same. If I drew that on a log graph, I bet you I could put a straight line through it of some kind and predict for you what the price of batteries would be in 2 or 3 years' time, pretty much. What's interesting about that graph is the price, because $100 a kilowatt hour, that is the point where you're almost at cost parity to manufacture an electric vehicle versus an internal combustion engine vehicle, there or thereabouts. So technically capable solutions. We've now got batteries at a price where I can make a vehicle, an electric vehicle, at the same price of internal combustion engine. Give it a few years, they'll be cheaper. They already kind of are, to be honest with you. We've also got very powerful permanent magnet machines using magnets like neodymium, iron boron. I think they sort of really came to prominence in the sort of 90s, late 90s, something like that, which means we can make electrical machines which are very power dense, very fast. I was watching some presentation from BYD, their latest generation. I think they do 2-to-1 field weakening, but their top speed is 30,000 RPM. And that's pretty spectacular. You can imagine how small the motor is now for something like 250 kilowatts or thereabouts. The faster it goes, the smaller you can make it. And you also need switching power electronics with high switching frequency power devices. And you're really starting to see that now. I mean, we used insulated gate bipolar transistors in this. We're now getting to the point, because of the automotive sector, where there is sufficient silicon carbide FETs that we can move to those economically. If we made the same inverter again using silicon carbide, it would probably reduce in volume by about a third, something like that. It's pretty spectacular. So here we have a situation where we have high oil price, which is funny because when I first volunteered for this, this lecture, it was February and the price of oil was dropping through the floor, and I thought, oh my God, electrification is going to slow down. And here we are a few months later and it's back through the roof again, and everyone's really interested in electrification. We've got cheap batteries, we've got technically capable motors and power electronics, but you also have to have the will to do it. Controversial slide. Oh, and it's not that controversial, is it? Because I think we all know now that when it comes to who's leading the world race in electrifying vehicles, it's not the US, it's not Europe, it's China. China has pretty much the world monopoly on mining and refining rare earth magnets like neodymium and a lot of other interesting metals like dysprosium. You put dysprosium in the magnets to make them higher temperature and not to lose their magnetism. China has the world's biggest lithium-ion battery manufacturers like CATL. China has, if you look at it, a very healthy manufacturing base for electric vehicles, very high penetration into their market, a lot of consumers, okay? And China has a strategic need to try and wean itself off oil. China doesn't have any oil, not really. It's got coal, it's got solar, it's got wind, it's got lots of oil storage, and the oil it does buy mainly comes from Iran through the Straits of Hormuz. That's not a good thing at the moment. They are not going to be swayed by short-term rises and fall in the oil price. They think long-term and strategically, and they will just keep on going. What does that mean for Western manufacturers? Well, they're going to be forced to respond. I Googled before I came here, what percentage of new vehicles being bought in the UK are electric vehicles? Does anybody want to hazard a guess?
20%.
20, it was almost 25, it was 24 point something. A further 11% were plug-in hybrid vehicles. And imagine that you're a vehicle manufacturer. I don't know, I won't name a vehicle manufacturer, but you've been enjoying this almost monopoly on making internal combustion engines. And in a few short years, and it has been a few short years, 25% of your market's gone. That's very serious. We now have plants, automotive plants in Europe that are now pretty underutilized. And what you're starting to see in the newspapers now is a scramble to do deals with Chery and BYD and whoever else will actually work with you to actually manufacture the Chinese EVs in plants in Europe. Plus that, you've got people trying to make real strides into making electric vehicles in Europe, like Volkswagen, although I suspect they probably did most of their EV work because it was a mitigation for Dieselgate, but that doesn't really matter. They're still going ahead and doing it, which is a good thing. And I don't think it matters if we've got certain, Western politicians wanting to turn the clock back and making rabble-rousing speeches, drill, baby, drill, because I think we've gone beyond that now. I think we've gone past the point of inflection. This is a technology change. It's disruptive. There will be winners and losers, but what history shows you is once something like that really takes off, especially when you get cost parity or there's some advantage, then it can change very quickly. I was actually shocked at the 24% penetration of EVs, you know, as in the UK today. So is electrification here to stay? Yeah, I think it is. I think it's inevitable now. I think it's gone the point of no return. Okay, I think I've taken my hour and a bit. Thank you very much for your attention. Really appreciate it. I hope there's some time for questions. Oh, questions.
Thank you very much. Lovely lecture.
Thank you.
Coming on with, teaches me a lot of things about how to make a lecture interesting. Talking about all the maths, coming on to the nitty-gritty of what we do now. That's got questions?
Well, two questions. One of which is really a point, is that 25% penetration is presumably 25% of sales during the last year.
Yes.
But not 25% of the cars on the road. Being
Absolutely
electric.
correct, yes.
The second one is, you haven't mentioned about dynamic braking and the failure, and which obviously is used in electric vehicles to extend range. Well, not only how does it do it, but what are the failure modes on that?
So this was another question that was asked. Basically, can you use a permanent magnet machine as a generator? Yes, you can. So, like I said, you can control torque by controlling, say, the Q-axis current. If I make the Q-axis current positive, I'll make a positive torque, and I'm motoring. If I just reverse that and make it negative, then I'll make a braking torque, and I'm regenerating. And all that energy will flow from the motor, from the vehicle, into the battery, and that will charge the battery back up again. Yes, and you can capture that energy from braking, absolutely.
Right, and you don't need any special inverter to do it, does
No.
the flyback diodes?
Well, the flyback dies are part of it, but they're really there for the switching.
Right.
But once you've got a grip of current, that's one of the first things my first technical director sort of drilled into me when I started working on electrical machines. Get a control of the current, because once you've got control of that, you can control torque and you can make it do what you want. You can do motoring, you can do regenerating.
Okay. But as far as the failure modes are concerned, I don't want to lose my brakes in the car.
You're never going to get rid of having real physical brakes.
Right.
You know, because of exactly what you've just said. If there was some failure and you didn't have mechanical brakes, you've lost your braking, that's bad. So, but what you would probably see is if you put your brakes on, your first port of call, as it were, would be braking from the motor, charging the battery up. And then if you really had to and you put your foot on the brake, then the mechanical brakes come in. But brake wear, as a consequence of that, on electric vehicles is pretty light.
Yeah. So the second one, does it matter if you're higher or lower than base speed?
For what?
For dynamic braking?
For regenerating, no.
Okay.
It doesn't matter at all. Any speed.
Did you have a question?
Sorry, yeah, I was just saying, does electrification only refer to vehicles?
Well, no, I work for Parker Hannifin. If you've never heard of Parker Hannifin, what they're really famous for is hydraulics. They make lots of hydraulics, a lot of which go on aeroplanes, a lot of which go on vehicles. So you can imagine now trash trucks, construction equipment, agricultural equipment, military vehicles, you name it. Wherever you've got hydraulic pistons doing things, there is a pump, usually connected via power takeoff to a transmission of an internal combustion engine that's providing that hydraulic power. As our customer base changes and electrifies, we've got to do it with them. So our solution to that is, well, we need inverters, we need to make and design permanent magnet machines, AC machines, and we'll use those to drive the hydraulic pump, to drive all the bits of equipment on the vehicle. That's what really drove Parker Hannifin to want to do this. And it doesn't have to be traction. There are other applications, absolutely.
What about train traction currently?
Well, lots of trains are electrified already.
But which technology, motor technologies?
Do you know, I don't know what trains use today. Certainly, there was another conversation before the lecture started. I do know that there are very large permanent magnet machines, for example, in wind turbines. I know people are interested in making fault-tolerant permanent magnet machines to make hybrid jet engines. If you're talking about a train, I mean, you're talking about 5-6 megawatts of power. I'm not sure if any of those are permanent magnet machines yet, but certainly if you see when you've got the engines on the motors on the bogies and it's distributed, I can imagine that those could be permanent magnet machines easily enough.
Okay. Did I hear you say that motors, well, you've got some motors go up to 30,000 RPM?
Yeah.
Right, I always thought the motors for vehicles were built into the wheels. But
No.
if you've got one of those, presumably you've got a gearbox and so on.
I was once told a story about, so normally in most vehicles, if you're talking about road vehicles, what you'll have is a motor that goes through a transaxle that brings the power out to the wheels, okay? And if you've got a four-wheel drive, it happens on both ends. There are people out there that want to put motors in wheels. Probably not a good idea to put your power electronics in wheels, but motors on wheels. But think about that. If I had a fault in one of those motors on one of those wheels, okay, I've suddenly got a seized wheel on one corner of my vehicle and I'm going at speed. That's not a good position to be in. That's why most vehicle manufacturers like the transaxle thing, okay, because it gets rid of that problem.
So I missed that. So the motors are inboard,
Yes.
but they're still what, solid on the shaft or some sort of gearbox between?
Typically you can see a single speed gearbox attached. There are some
differential.
yes, goes through a differential, yes. Thank you. There are some vehicles now, I noticed, that are coming out on the market that might have, say, 2 speeds, okay? And generally speaking, they don't have clutches. And generally speaking, they don't have reverse gears either because they don't need them, because you can just tell the electric motor to go backwards. It's a simpler proposition.
Which is a follow-on question. I was, a few months ago, there was on TV or somewhere, there was a car which was built specifically to do the quarter mile in the shortest time and shortest 0 to 60 and go beyond it up to 130 miles an hour. So, and they used one motor, or I can't remember exactly, they may have used 4 motors on that. No gearbox, no nothing.
Yeah.
Now, was that a dangerous car from what you've said?
I've heard of certain manufacturers that have, say, 2 motors at the front and 2 motors at the back, but they still go through some sort of transaction differential gear, yes.
Yeah, okay. But what, you mentioned for that inverter 4 to 8 kilohertz or whatever
Yes.
it is, but the inverters for these kind of cars have got to go from about 1 hertz to 30,000 or whatever is equivalent.
So we have a rule of thumb,
Yes.
which says I need at least 6 PWM cycles per electrical rev.
Okay.
And that kind of sets the limit.
So what's the typical slowest to fastest on that?
Depends on how many pole pairs your machine has.
Yes.
If you've got a machine with a very low pole count, 2 pole, 1 pole pair, 2 poles, then you don't need a very high output frequency to support a high speed on your machine. It's one of the bugbears of having lots and lots of poles in your machine that to get any decent speed, you need a really high output frequency. But I think, the world is changing now. As I said, we've kind of got to this point. Silicon carbide FETs, which switch really quickly, and you can switch them at 20 kilohertz and beyond, used to be really expensive to buy. Now, the volume is there that they're actually getting very economical. And in fact, you can save on other aspects of your design by switching quicker. As you can probably imagine, magnetic components get smaller. So if you've got sort of EMC filters in here, trying to filter out switching noise, the faster I can switch, the smaller I can make these things. So the future is, we're on that cusp of changing switching technology, and we're going to end up switching quicker anyway. It will be 20 kilohertz plus.
You got a follow-up question? Question stroke comment, really.
Yeah.
I was surprised the other day to see JCB going over to hydrogen.
Yes.
Also hydrogen where you've got to store the hydrogen, you've got big heavy tanks, etc. But they had about 4 tanks, a lot of carbon fibre and so on, quite small,
Yes.
and that was enough to power a digger all day.
Yes.
So I'm just wondering whether there might still be some prospect of keeping internal combustion engines.
I'm not saying there isn't, to be honest with you. And Lord Bamford makes a really good point. You know, batteries are heavy. So if he wants to make a 30-ton digger today, by the time he's put the battery in, it's probably a lot heavier than that, which is why he's very keen on the idea of hydrogen combustion engines, because it's clean and you keep the combustion engine and it's lighter than a battery. Having said that, there are diggers made by JCB today, little mini diggers, that are entirely with batteries. And the reason for that is typically because there's some sort of legislation that says, I don't want a diesel engine running in the middle of my city. I want this to be nice and quiet and pollution free. And so there is a market. But I do tend to agree, there are some things, I mean, shipping, for example. Can I really imagine shipping's going to be run on batteries? I mean, people are trying, don't get me wrong, but it's difficult to see. So in that point of view, cleaner fuels and internal combustion engines are not a bad thing. But you can definitely see, for you and I, electric vehicles running around Worthing, even on long journeys these days, is actually quite practical to do.
You talked about control of motors. How do the different manufacturers differentiate themselves in the market?
That's a really good question. There's not an awful lot different in the way that we all our approach to controlling motors, because the motors are essentially the same, the physics of the motors are the same. You can try and add extra features into your product. I mean, for example, I work for a company that does lots of hydraulics, so it wouldn't surprise you to know that we're very interested in putting hydraulics control directly inside our inverters, you know, and making a value add in that sense. Some people make quite a thing about the accuracy of the torque they can produce for traction applications, so they're all different. Some people compete purely on price, so it's a mixture.
This is another thought on applications, might be outside of your experience, with things like bearings for sort of no or low friction, or maglev, so I guess it's kind of a linear version. Is there some potential there that's being exploited? Or?
What, for magnetic bearings and linear?
Particularly for permanent magnets.
I know there's a local company that does sort of magnetic bearings, and I'm not quite sure how they do those. The linear machines I've seen tend to be more like the type of induction type machines. I've not really seen them with permanent magnets in, but maybe there are examples out there. It's not something I've been part of, to be honest with you, so I can't really answer that honestly.
So the question is, in the context of, let's say, failure mode, a failure mode,
Yes.
obviously all the failure modes you've discussed is about it kind of stopping. In certain applications such as subs, where you can't have the, let's say, mobile pump, you can't have it to stop, how would you control the DMM without the inverter?
There's lots of research at the moment, especially in sort of aerospace applications, where people are trying to make fault-tolerant machines. And for example, good aerospace, I mean, I've seen a couple of examples of this now, where effectively you try and build 4 motor windings in one machine and have 4 inverters. And the idea would be, if there was a failure in one, you'd somehow contain the fault in one, but the other 3 could keep the thing limping on. The challenge there is failure rates. I was quite surprised to hear that the failure rate of gas turbines is like, or the fit rate is like 10 to the minus 10. So next time you're in a jet plane, think about that. You know, the chances of that thing going wrong are practically 0. Whereas I can't say that for an electric motor. They just can't reach that sort of level, which is why there's this interest in, can we make fault-tolerant motors and inverters, because then we could push, you know, the failure rates up to the sort of thing that aerospace needs.
It's a comment, really. The point, well, it links into your last point about, is electrification here to stay? The Lower Thames Crossing, which is a large new tunnel outside of the Dartford crossing, the organisation promoting that is trying to do it at zero carbon, and they are using hydrogen in a lot of their plant. And one of the use cases they've got is running the site generators. How many times do you walk past a site that's often in a town that hasn't wired up to the network, and there's an on-site generator?
Yes.
And that's a good example of hydrogen.
Yes, it is.
And it really, the point that links to is, I'm very surprised that is electrification here to stay doesn't include reducing climate change.
Yeah, it could have done. I must admit, I could have easily put that in. You're right.
It feels a central reason for why a lot of people, I think, are purchasing.
Do you think so? I think the thing that really pushed people was all the stuff that's coming into the air, especially through diesel. But I think that really caught people's imagination at some point. It was the pollution that was being created. And now, quite frankly, it's just financially sensible.
I mean, China had a terrible air quality
It
problem
does.
in cities
Yes.
with coal burning.
Yeah.
And so I think that drove some of the strategic thinking.
Yeah.
Mike, then yourself?
Formula One E motors, or the assist, not Formula E, but Formula One with the which is a hybrid engine,
Yes.
essentially.
Yes.
Are there any obvious trends that's going to happen there, or do you think? Or?
We're not really involved in Formula One, unfortunately. We're more involved in things like JCB, to be honest with you.
Okay, I've got various engineering friends, and when they heard I was coming to this lecture, they said, ask about trapezoidal control. Is
Yes.
trapezoidal just the shape of the waveform, basically, which is what you've shown us?
Trapezoidal control. Is that 6-step, Paul? I can't remember trapezoidal. I think it is. I think it's a 6-step control, is a trapezoidal. Like I say, 6-step is quite a common control technique. Air conditioning units used to use it because it was quite a simple type control system. It's quite easy to do. There are variants on it where I don't use all 6 switches. I just use 4 switches and leave the third one not connected, and then just move those around. You get less volts out of it, but obviously you reduce your losses when you're doing it. So
Thank you. I think, are there any more burning questions you'd like to ask? Otherwise, I'll wrap it up. Is that okay? Yeah? Would this box encompass what you've been talking about,
yes.
in a sense, that Paul has been involved in at the back? Would you say that what you have here is that you have a battery supplies to DC? This is the magic thing that powers your 3-phase motor.
Yes.
So that's crucial. And that's why I think I got away from this thing today. That although we had the maths and things like this, it was really good to hear your design issues relating to the maths, which is really nice.
Yeah.
You know, and how you get onto it. And you're saying that if you use silicon carbide, this could be this big.
Yeah. Its volume would probably reduce by about
Which is
a third.
really
Yeah.
good. So I found this really interesting. So I'd like to,
Do you have to connect a hose to that and water brush?
Yes, you do. No, honestly, you do, because it is liquid cooled, just like an engine. So those are the way you put the water cooling. Yes. Otherwise,
What sort of temperature rise do you see in the water?
well, it depends. This thing's meant to run with a sort of like an ambient temperature of 60, 65 degrees on the.
only a couple of degrees.
It's not a huge amount of temperature rise in it, but yeah, you do need a cooling circuit. Otherwise, you couldn't make it that small.
Well, thank you very much. Before we do the clap, this is the acknowledgement. Dave produced it and Mike signed it.
I get a
For you.
certificate. How cool is that?
Not only that, you got an IET power bank. I don't know how powerful this is. But
I didn't know I was going to get
IET, so
rewarded.
can't
This
be
is
much.
really nice. Thank you very much.
there's something to remember this by. But
Oh,
could
thank
you
you.
please join me in thanking David Blood.
Thank you very much indeed. Thank you. Thank you.
Thank you very much.
Thank you, Jesse. Thank you.